Yes?
What is y?
Y is just an element. So again, let's recall what we have talked about closed sets. So what does it mean for a set to be closed? By definition, complement of that set in M is open. And what does it mean for the complement to be open? It means that as long as I find an element y, any element, which is not in F, not only is it not in F, it has an insular neighborhood surrounding it. So there is some epsilon center in a ball centered at y, where the full ball is in F complement. Is that clear? So that's what it equates to. So the complement is open means that for any point that you don't find in F, there must be an insular neighborhood around that point, which is part of not F. And what does this amount to? This amounts to this. So if X is a member of the set F, then the implication that any neighborhood that I can try to surround X with cannot be an insular neighborhood. It cannot protect X against members of F. So that means that the intersection of the ball of radius epsilon around X with F is never empty, no matter what epsilon you pick. Good? And what does this lead to? This leads to considerations of what it means to be insular and what it means to be not insular. So what we would say is the following. So you can say that if you just are getting any set A and pick any x in the metric space M, then this x is a limit point of A if the following happens. If the ball of radius epsilon around x minus x, this means punctured neighborhood. This is called punctured neighborhood of x. And when you intersect it with A, that's not empty no matter how small is your epsilon. And intuitively this means that x is arbitrarily close to friends of type A. So that, you see, why do I puncture x out? In other words, the intersection might not be empty because x itself might be a member of A. And I want to eliminate this from consideration. Is the ball of radius epsilon, does it contain other members of A with the possible exception of x? You understand? That's why I puncture it out, so that I don't take it into consideration. So x is arbitrarily close to friends of type A, and then we can make the following definition when that doesn't happen, and that's called isolated point. So you would say that, again, let A be a subset of M, and we would say x belonging to M is an isolated point. Maybe I even can say, I'm not sure, you can take x belonging to A. Maybe he is isolated. An isolated point of A if ball of radius epsilon centered at x minus x. In other words, the punctured neighborhood intersects with A trivially. And that's for some epsilon bigger than 0. Okay? And hence the quotation marks about friends. Yes?
X is in M, can X also be in A? Or is X
well, so x is in M, it could be in A or it could not be in A, I don't really care, right? What I'm saying is that he is not arbitrarily close to other members of A. When I say other, maybe he is a member, maybe he is not a member, but he's not close to other members of A if this happens. If the intersection is empty, then we have an isolated point. And if the intersection is never empty, then you have arbitrarily many members of A right next to this x. Yes?
Does that mean every point in A is a limit point?
I don't know what A is. This is all I'm saying is this, right? I'm saying, how do you check if a given point in M is a limit point of A? You look at that point and you draw a neighborhood. Okay? You take so let's say this is maybe A looks like this. So this is our M. I draw it as a square, but you know, it's just some space. This is M, and A would be some region here. Okay, so it's this region, and this region, and this region, and something like this. Okay, so this solid region. So then I might ask, which points here are not isolated. So for example, I can pick this point here. I can take this point to be x. In this case, I picked a point in A, right? And I'm asking, is this point of A isolated or not isolated? So it is clearly not an isolated point. It is a limit point of A. Why? Because I can select, no matter how small a ball I select, so I can select this ball. Okay? Notice it's a dynamic property. The fact that I can select a full ball that contains only points of A, that's not good enough. Because, well, after this ball I need to select a smaller one and a smaller one. So I have a bunch of concentric circles around X, and if the interior of each concentric circle intersects with A, then it's a limit point. Does it make sense? You see what happens, right? So for any epsilon, I check, this is epsilon equal to maybe 1, then to 1/2, then to 1/3, and I see that no matter how small is the neighborhood, the intersection with A is not trivial. So this X is a limit point of A. Okay, so this is A. Okay, this X is a limit point of A. Okay. Now I can select this Y here. Okay, this Y, in the drawing I'm assuming this Y is not part of A. But you can see that I can take any concentric circle around Y. And this concentric circle, although it will intersect with not A, it will always contain A will have breached the perimeter of that circle. It always contains points of A. So this Y is also a limit point of A. Okay? Now let's say I'm gonna just to illustrate, by way of illustration, I will add this point here, and by marking it red, I'm saying it's part of A. So this point is Z. This point is Z. And notice what I can do. I can surround this point Z in such a way that nothing but this point Z is a member of A. I found just one neighborhood. Just one neighborhood, and this one neighborhood, if I puncture Z out, it has no elements in A. So then I can say that Z is an isolated point. Make sense? Now, if it does make sense, tell me, if my metric space is finite, could there be limit points in that metric space? Could anything be a limit point of anything? If the set is finite, kind of like members of this class, right? If I consider the set of points, if I maybe take a photograph and I consider the set of points which are the individuals sitting in this class, could any individual be a limit point of any other points? Yes or no? No.
Because they're in the class.
Because notice when I do this, when I use this epsilon, epsilon is real. I can always create a small enough open ball centered at you, provided you're a point, and this neighborhood intersects no other members of any set that I specified. If it's finite, I can make a ball small enough such that it only contains that one point. Do I make myself clear? That's why I say friends in quotation marks, because unless your space is infinite, you have no friends. Never. And that was the issue of the last lecture. Good? So from this observation, look at this. What's the requirement for a set to be closed? The requirement is that whenever a point is in F, the neighborhood around this point when you intersect it with F is not empty. So let's see. Do I need to say more about it? So notice the following. So if X is a limit point of A, if X is a limit point of A, then there exists a sequence of distinct elements of A such that A sub n goes under the metric space D to that point X. Do you see why? What do? You can just observe this by saying that, okay, so if I take ball of radius I can take ball of radius 1 centered around X and puncture out X, and I can take the intersection with A. That would be not empty, so pick A1 in the intersection. So you can pick A1 in the intersection. Next, I can select a ball of radius 1/2 centered at X, and if I puncture out X, by the condition that X is a limit point of A, the intersection will still not be empty. And therefore I can pick A2 in intersection. Okay? I'm a bit lazy to write it full out. If I need to, I can guarantee that A2 is not equal to A1, because instead of picking radius 1/2, I can pick radius to be equal to minimum of 1/2 and the distance to A1. Okay? So I can make it smaller if needed. Not 1/2, but the minimum of 1/2 and the distance to the first point I picked. And that eliminates this point. That creates a radius smaller than 1/2 or equal to 1/2, I don't know, depending what's the minimum. And in that neighborhood, A1 would be excluded, so then A2 is distinct. I'm just lazy to write it, but you understand my point, yes? Yes? And in general, I can take ball of radius 1/n centered at X, remove the point X, take the intersection with A, that will have to be not empty because it's a limit point, so I can pick a sub n in intersection. So it is obvious that, that the sequence an will converge under the metric d to x. Because you can see that they are clustered, right? How do we notice convergence around x? Well, we see clustering. For any epsilon, I pick 1 over n smaller than the epsilon by Archimedean property, smaller than epsilon, and all but finitely many of my ans will be clustering around the point x.
Professor, and the sequence can be finite or infinite, right?
Well, that's what I'm again asking. What's the sequence? Is it finite sequence or is it necessarily infinite?
It can be either.
Well, look at it carefully. Could it be either? Look at the argument again. Look what are we doing? What am I describing? I'm describing this concentric circle procedure. So you see what I do? I take this point x, and provided it's a limit point, or let's say this y, provided it's a limit point, I can select a neighborhood starting at 1. There will be a point other than y that is inside of this neighborhood. Then I can shrink to a smaller circle around y, and that will be small enough, maybe smaller than 1/2, and small enough not to contain the first point I picked. And still, by the property of being a limit point, it has to contain another point of the set A, distinct from the first, then shrinking more, distinct from the first 2, shrink more, distinct from the first 3. So could that sequence be, could it have a finite range? Could it be a sequence of the same point or not? What's the range? How many points do I pick? All of them are distinct. This is a sequence of distinct, and therefore it's an infinite sequence of infinite types of points, infinitely distinct points. You see what I'm saying?
I think I misunderstand what a limit point is, and that's why.
Yes, the problem is the word limit, and it suggested that this sequential definition is a little bit, it seems when you say limit point, the sequential definition is suggested. But the word limit point, forget about why it was formed, only means that that a point is arbitrarily near the set. So when I say x is a limit point, then in your head, of what? Of some set. And what does it mean? It means that this x is arbitrarily near members of the set A.
Yeah, but in the definition you write for any epsilon greater than 0. So I could pick a point really far away.
For any means for all. So you pick whatever epsilon you pick, the neighborhood that is centered around the point that you picked with that radius, it will intersect, just like in the picture, with the set A. It will intersect with the set A, and the reason I move out x is because the intersection might be like in this case, right? The intersection might be the point itself, right? The point itself is not quite a party; it needs friends.
So by any you mean all, because any.
Yes, that's actually exactly what it means. By any I mean all epsilon. But when you say pick all epsilon, you're not picking them all at the same time. You pick some epsilon, and whatever epsilon you picked, that ball will intersect with A. Make sense? It's going to be important. I mean, when I talk about everything that follows, we have to understand it. Good? So, what then did I just show? I showed this relationship, that when you have a limit point, you can generate a sequence. You see, limit point in a metric space, by the way, that's not true when you study arbitrary topology. When you don't have a metric function, that's going to be even weirder. But in a metric space, whenever you have a limit point, that implies the existence of a sequence of distinct elements. The sequence has to be infinite. In particular, if A is a finite set, could it have any limit points? If A is a finite set, could it possibly have any limit points? No, it couldn't. Because, you see, if it had a limit point, I could generate infinitely many members of A. Because, you see, I generate infinite target with the concentric circles. Make sense? Something bothers you. What bothers you? Concentric circles. They basically, what I imagine when I say that, let's say, y is a limit point, I imagine a bunch of concentric circles, infinitely many of them, and each concentric circle contains a point from A, which is not the center of any of those circles. They're all centered at the same y. Okay, and that is what a limit point is. And then, what does it mean? It means that that I can then select those targets small enough so that basically between the two circles I select a point. Between the next two I select another point. And that generates a sequence of an infinite sequence of distinct elements. Okay? So, conclusion. A having a limit point implies several things. So it implies first there exists sequence an in A such that an converges to X. And the second part that it implies is that this the sequence can be picked to be infinite. And the third thing that this implies, that to have limit points, A must be infinite. There is no way about it. Based on the procedure that we just generated. So, if I ask you on the test, here's a finite set, and it's given some crazy metric. Could this set have any limit points? The answer is no. Notice I always ask about sets. When I say what has limit points, those would be sets. Sets have limit points. And that's maybe why the word is a bit confusing. You might think of limit points as certain limiting conditions on a function or who knows what, right, from calculus. But the limit point, all it means is arbitrary proximity to a set. So now a question, and I actually already asked this last time. Question. If A has a sequence let's call the sequence as before A sub n, and A sub n goes under the metric D to the point X. So I'm still having some metric space in mind. A sub n goes to X, it converges. Is X a limit point of A? Why or why not? You see what I'm asking? So what I just verified is if I have a limit point, that implies an existence of a sequence that converges to that limit point. Now I'm saying now I have a sequence that converges to a point. Does it make X a limit point?
If A is infinite, yes. If it's not infinite, no.
Wonderful, that's exactly the answer. So if if the sequence, and not even not just A, but the sequence itself, an is infinite, then X is a limit point of A if A sub n is finite. If A sub n is finite, I should be very careful. If A sub n is finite, then X might not be a limit point. Why I say might not? Well, A sub n is finite, maybe I can find another sequence which will be infinite. And then the answer will be still yes. But if the sequence itself is finite, well, it doesn't work. Okay, so an example perhaps. So let M be R. And you understand what I mean? That means I give it the default metric. So let M be R, and A equals, let's say, 0, 1, including 1, union 2. Okay? Union 2. So then, you can take for example, you can take A sub n to equal, let's say, simply 1. Okay? If A sub n is simply equal to 1, then obviously A sub n will converge to the point 1, which is an element of A. But this was not a verification that it's a limit point. You see, because I'm just standing at the same point in the sequence. Okay? But on the other hand, I might say B sub n equal to 1 minus 1 over n. 1 minus 1 over n, and then I have that B sub n converges to, so I then have that B sub n is an element of A, and B sub n converges to 1, which then implies that 1 is a limit point of A. Okay? So that's an example of what I'm talking about. Okay? So 1 is a limit point, and I just easily generated, in this case, a sequence. Okay? But if I just select a finite sequence, it may or may not be a limit point. So in this case, the sequence is just a constant at one number. That's how a finite sequence can converge. It's either finite or eventually finite. Okay? And another question is just what are the limit points of A? What is A prime? A prime, which is a set of all limit points. Of A. Write it out. So here A prime is only taking membership, is only accepting a membership if the element is a limit point of A. So what's the answer? It's in R. What are the points that are at arbitrary proximity to A?
I want to say all the points in A, but it doesn't have to be in A to be a limit point.
So remember what makes a point not a limit point of A if the point stands alone. If a point stands alone, it's not a limit point of the set. Okay? Because to be in arbitrary proximity means excluding myself, do I have friends around me of my type? Or of type A, they don't have to be of my type. Yeah?
0?
0 is 1, sure, but I asked for all of them. Give me all of them right away.
Anything from negative infinity, 0?
No, so you're giving me way too much. Minus infinity, so is let's say for minus infinity, is minus 1 a limit point? Is the set arbitrarily close to minus 1? Yes?
Well, I thought you were talking about any A, but if we're talking about A is the union of 0 to 1 to 2, then it would be just from 0 to 1.
So at 0 it's open bracket, should it be open or closed? So is 0 included or not? So what is the set of all limit points?
0 is included.
0 is included. So the answer is A prime is simply equal to a set 0, close bracket at 0 and 1, and I must give up, I basically must eat the point 0 and give up the point 2. Yes?
Is it the set of all intervals in A?
The set of all intervals in A, that's true as well, but yeah, that's true as well, but then, careful, because all the intervals in A don't contain 0, so you need to edit. You see, so you're almost right. So if you say all the intervals in A, that will still not include 0. So you see what we had to do? We had to give up the party pooper, the lonely guy, and we had to include this 0 because they want this A wants to make 0 a member of the club because it's arbitrarily close to it. You see, can you imagine it? I don't want to draw it, right? So every point, if I select any point between 0 and 1, I can select a small enough neighborhood that it's wholly contained in 0 and 1, and therefore every smaller neighborhood will be wholly contained, and therefore every point in here will be a limit point. 1 is easily a limit point. 2 easily is not. I just select radius 1/2 around 2, and that only contains 2, so he is lonely. Good? That's the answer. Everybody understands it. Wonderful. So let's write out this theorem, which I hope it's very intuitive already. And that's a characterization of closed sets. Theorem let F be a subset of MD. Then the following are equivalent. So, condition I, F is closed, and of course I mean in M, right? The word closed means nothing unless you have your universe specified, or you have it by default. F is closed, that is F complement, which is M minus F, open. So that's the definition we just gave. Second condition is notes. If ball of radius epsilon around X intersected with F not equal to the empty set, for any epsilon bigger than 0 implies that X is an element of F. condition is, I will give a sequential condition. So if any convergent sequence x sub n part of f implies xn going to x, that means x is a member of f. So those are the three conditions. So I have a condition in terms of open sets, in other words this property, and that implies immediately property 2, and then we have property 3. I'm a bit lazy, but I guess I will write out why this is true. Proof. So what I'm saying is that you can take either item 1, 2, or 3 as your definition of closed set, and all the others are immediately given. They all imply one another. Okay? Proof. So first I observe that condition 1 implies condition 2. And why that is the case? Well, so f is closed. So if I have ball of radius epsilon around x, intersection f always empty, epsilon bigger than 0, that means that no ball of radius epsilon around x is part of f complement, and that means that x is not part of f complement, which means x is in f. So also many words, that's very simple. What does it mean? To be a closed set, the complement is open. So complement protects every member of any element in its herd. Okay? So then I ask, could this x be a member of the herd? And the answer is not, because it's not protected. You see? For no epsilon is it protecting x against f, so it could not possibly be a member of the herd f complement. And therefore, if it's not in f complement, it is in f. Yes? Clear? So now we look at how 2 implies 3. So we now assume that, we assume 2, and we see how that implies 3. So I'm assuming that this condition is true. So I take a sequence. Let xn be a sequence in f such that xn goes to x. My goal is to show that this implies x is a member of f. So how do we go about it? So we look at, so we have this. So we look at the ball of radius epsilon centered at x and intersect it with f. Could it possibly be empty? Well, this intersection, it contains ball of radius epsilon around x, intersected, instead of intersecting it with all of f, I only intersect it with a smaller set. So you have this container. So it would be just the sequence xn. You see, instead of intersecting with all of f, I intersect this ball with the sequence xn. But the sequence converges to x, that means that this intersection cannot possibly be empty. So this is not empty for any epsilon bigger than 0 by 2. That implies x is a member of f. Okay? So 2 implies 3. See, if I have this second condition that f is such a set that whenever you pick any x in the metric and you find that you cannot protect this x against f, f will eat it. That's condition 2. And condition 3 is suppose that you find that a sequence goes to some x, then if that sequence goes to x, then f must eat the convergent of that sequence. So we see that that 2 implies 3. And then finally, to close the loop, I need to show that 3 implies 1. Implies 1. So what am I now assuming? I'm now assuming that f is voracious on the convergence of its sequences. So how does it imply it's a closed set? So what we do is this. We can see that so that x belong to f complement. So if I want to show that the set is closed, I'm considering the complement. If x belongs to the complement, I'm going to show that no sequence can get to it. Okay? So if x belongs to f complement, then there must be an epsilon bigger than 0, such that the full ball of radius epsilon around x is part of f complement, for otherwise I can look at the sequence ball of radius 1 over n in x, and I intersect it with f, and if this happens to be not empty, then there would be an element xn belonging to the ball of radius 1 over n around x, intersection with f, which then implies that xn, which is a sequence in f, with xn converging to x, which when then by 3 implies that x is a member of f, which would be contradictory to our assumption that it's not. So many words used. Really, why are all those things really obvious? Okay, all of those are different descriptions of what it means to touch. This means, what does it mean for f to touch something? So if x cannot be protected from f, then that's one way in terms of open balls to say that f touches x. And if it touches x, it eats it. Right? And condition 3, there's another way of considering touching. Right? So let's say I touch this bottle, so what you do is x1, x2, x3, x4, x5, x6, etc. So you can see I can generate a sequence that goes to the point I'm touching. So you see, all those conditions involve touching, and a closed set is closed as long as whatever it touches, it eats. Very easy. So what we now need to speak about is closures and interiors. That's the next word. It's too bad. I might not get today to that point that I wanted to speak about. So let's see. So closure and interior. So what we have is, given metric space MD, if we have a metric space space empty. I want to know and A belonging to M. The questions I have the first question is what is the smallest closed set that contains A? So that's one question. A second question is what is the largest open set? Contained in A. So that's what we consider now. Two questions. One of them, I have a set A. If the set A is closed, that's the smallest closed set that contains itself. If it's not closed, we need to feed it some points and maybe make it closed this way. Allow it to eat some points it touches. And the set A might be open, in which case the largest subset that is open will be A itself, or it might not, and that means giving up some points that cannot be protected. Okay? So to be open, what you do, you throw out what you cannot defend. To make a set closed, you eat up the things that you touch. That's really what's going to happen. We're going to see this again. Make sense? So we define, so for one, we can say something like this. So we have closure of A. Often it's much nicer to write as A with a bar. It's called A closure or closure of A. And I can define it by saying that A bar is just the intersection of all F such that A is a subset of F. Maybe I should say it like this: the intersection over alpha of A alpha such that A is a subset of A alpha, and F alpha is closed. Again, never forget we are in M. The word closed by itself is meaningless. You always have to refer to the universe. Okay? So why is this a good definition? So you see what I do. I take all the closed sets, I intersect. So first of all is notice that A bar is an arbitrary intersection of closed sets. Which makes it closed. You remember this property. If I take arbitrary intersection of closed sets, I can take the complement of that arbitrary intersection. That will be union of the complements of F alpha, and that's an arbitrary union of open sets, and therefore the complement is open, and the intersection is closed. So A bar, or closure of A, is closed. That's the first thing we know. Also, A bar is the smallest closed set such that A is a subset of A bar. Why is that the case? Well, if C is closed and A is part of C, then we see that C equals to one of the F alpha already. So what I mean is already part of intersection. In other words, what I'm saying is that C, which is equal to F alpha, contains the intersection over all alpha F alpha, which is a closure. So you see, if I take a closed set, the closure of A is already inside of that C. Does it make sense? Because I took the intersection of all of them. So take any closed set that contains A, then by that condition that I intersect all the sets that are closed and contain A, C is one of the things that I intersect. So C is equal to F alpha, and F alpha will contain the intersection of all the F alphas, right? Because when you take intersections, you only make the set smaller. So it's at least as big as F alpha and possibly smaller. So you can already see that C contains a closure. So the smallness property is justified. Okay? And 2. I can define interior of A more often and simply written as A with a circle on top, and this means interior of A and that's defined the following way. So interior of A is defined as the union of all G alpha such that G alpha is an open subset of A. So the way I'm going to try to produce the maximal open subset that is inside of A is I'm going to find any open subset in A and I'm going to take the union. And by taking the union, you are clearly growing it. Okay? So you can see that this is the biggest. This is open. So the interior is open because union of open sets. So this condition is trivial. Taking arbitrary union of open sets doesn't change the property of being open. And the other part is A sub 0 is a subset of A. That's clear because we're only unioning things in A. A0 is a subset of A, is the biggest. Open subset. Why is it the biggest open subset? Well, if I have any G belonging to A, G open, then G already equals to some G alpha. Because we already considered, we were taking all of them together, G is equal to G alpha, and therefore what we have is, we have G equal to G alpha, which is a subset of the union over all alphas of G alpha, which is a subset of A. Okay? Or I should say, and this is equal to the interior, and that's a subset of A. So this solves it discussion, but it's not always useful to consider intersections of closed sets because you don't necessarily know all the closed sets. And it's not always useful to take the union of all the open sets because you might not know all the open sets. So we need some other characterization. So if you look at 1, so let's characterize 1. Let's characterize the closure. So we can say that X belongs to a closure if and only if what must be true. So you understand, I had a set A and it was turned off, it was not right away voracious. And when I take the closure, I make it a closed set. When I take the closure, what am I really doing? I'm making it a closed set. What must I give it? So X belongs to a closure if and only if what? If and only if either X already belongs to A, right? Closure only grows the set. So if X already belongs to A, it must continue to belong to A. I cannot throw it out. Closure has to be bigger. Okay? Closure, I'm taking a set and I'm making it closed, and therefore making it bigger. Or what? Or what's the characteristic? Now A bar must have become a voracious set. X must have been what? If I actually had to add X, in other words, X was not itself part of A, I had to add it. What must be true about this X? It was what? Limit point, exactly. Okay? Or X is a limit point of A. Why, if it were a limit point of A, it had to eat it. Okay? Well, you have to be very careful here. Does this show that this is indeed a closure? I need to prove it. Because, well, you see, I definitely have to feed all the limit points of A, but maybe once I fed more points, now this new set with the limit points of A is bigger and it has further limit points. Okay? So I have to be careful there. So, claim, that's what I'm saying. Claim is that A closure is just equal to A union with the limit points. Okay, so you remember that A bar limit points of A. Okay. Let's try to verify it. So proof. So I'm going to label this as H. So H is going to be A union the limit points of A. So all I need to verify, so first I need to verify that it's a closed set. I don't need anything else. So then H is a closed set. In M. How do I know? Well, so pick Y that belongs to H complement. I want to show H complement is open. Take Y belonging to H complement. That implies that Y is not a member of A, and Y not a limit point of A. And by knowing that it's not a limit point of A, what do I have? I have that there must be an open ball epsilon bigger than 0 and a ball of radius epsilon around Y with intersection A equal to the empty set. Do you agree? So I'm trying to show that that it's enough to add the limit points of A to make the set closed. Now what I do is I call A union the limit points, I call it H, and I verify that H is closed by looking at the complement. So I look at H complement. If I look at H complement and I find Y there, in particular Y is not a member of A, and Y is also not a limit point of A. What does it mean? It's at some distance from A. That's what this is saying. The intersection with both epsilon around Y and A must be the empty set. You agree?
It's an isolated point.
Yes, you can call it, I suppose. I don't remember the precision of it, but yes, but it's isolated away from A. Sure, right? It's isolated from A. So its intersection with A is the empty set. And now I want to show that its intersection with A bar is also empty. Furthermore, if ball of radius epsilon, the ball around Y, and intersection with A bar isn't empty, then ball of radius epsilon around Y contains a limit point A bar of A. So to illustrate this in the picture, so here is that ball. This ball is centered around Y. And suppose that this is ball of radius epsilon. And what I'm claiming is, so you see, the first part, I know that there are no points of A. Now, in order, what I want to verify that this ball also doesn't intersect A bar. So in other words, then I know the full ball is not only in A complement, but also in the complement of A bar prime, of A prime. So what I'm saying is, suppose I did somehow find the limit point A prime, and maybe the limit point is right over here. So this is A prime. Okay? Then what must be the case? A prime is a limit point of A. Then I can select a ball around A prime small enough to fit inside of this big open ball.
Why do you need to take the union of A and A prime? Why isn't it just equal to A prime?
Why the closure?
Yeah.
Because you notice, remember that example where we had 0, 1 and 2 isolated? Now remember that when you looked at the limit points, you had to toss away 2. 2 was not a limit point. When you take the closure, you always add points. You never toss a point out. Remember the interval is 0, 1 with 2. We looked at the limit points. So you're now asking why is it not just limit points? If I only look at the limit points, I include the 0 and I throw out the 2. Closure never throws anything out of A. Remember, it takes A and just feeds it something to make it bigger. It's supposed to be a closure. You're supposed to find the smallest possible closed set which incorporates in itself A.
So is two a closed set on its own?
Yes, 2 is a closed set on its own. Any finite set is closed on its own. So what I now do is, you look at it. So I notice that there is a ball that is insular away from A, and now I need to show that it's insular also from A prime, and then I can conclude that Y has a protective neighborhood away from H, which includes protecting against A and protecting against A prime. Okay? So here is the picture. So follow this picture. So there will be a delta here. Delta, and then because this is a limit point, this is arbitrarily close to A. So there must be a point in A somewhere here. In the picture, that's what's going to go wrong. You understand? I already showed that this ball contains no elements of A. Now I'm just to be formal, I'm showing, well, it cannot possibly contain limit points of A, because the limit points, they drag after themselves members of A. So what I imagined when I first looked at this theorem, I imagined a fisherman, right? He's throwing his hook. So the limit point is that fish that swims, and the fisherman, since it's a very big fish, is dragged after it. Okay? So if the fish, which is the limit point, enters this ball, then the fisherman, A, is dragged into the ball. That's really the argument. Okay? Yes?
But that point A prime, little a prime,
Right.
does not have to be a member of A.
No, it does not. Because it is a member of A, I don't need to worry about it. By what I already did, I showed that the neighborhood of radius epsilon is protecting Y against A, but it needs to protect also against A prime. Okay? To show that H is a closed set, I need to protect any point in the complement against both A and A prime. So I have this. So if this intersection with A prime is not empty, then the ball contains a limit point A prime of A, which implies that there's going to be a ball of radius delta around A prime, which is part of the ball of radius epsilon around Y. That's the blue ball that I drew here. And what does this imply? This implies that A belonging in A will be in, so maybe I should say A belonging to A. It also satisfies that A belongs in the ball of radius delta around A prime, which is in the ball of radius epsilon around Y, which implies that the ball of radius epsilon around Y intersecting with A isn't empty, and that is a contradiction. So again, I hope I spelled it well enough for you, but you understand what I'm saying, okay? So first argument is Y belonging to the complement implies Y cannot possibly be an A, implies that that there is an open ball around Y, and its intersection with A is empty. So that's the open ball. Now suppose somehow this intersection happened to not be. You can maybe even argue simpler. Take the complement, it will be A complement intersection A prime complement, right? Maybe I just made too much of an issue here. You can just maybe just right away just take complement and see that it cannot also contain this. Oh, anyhow, so the argument I just wrote, you follow it. So if A prime is a limit point that happens to be lured into that set, that implies that no neighborhood of that point isolates A prime from A. So that will lure members of A into that set, which is impossible, okay? So the conclusion is the class is over at 6:50, correct? So what do we get? So that implies now that B of radius epsilon around Y intersection H is empty, and therefore that the ball of radius epsilon around y is wholly in terms of H complement, which then implies H complement is open, which then implies H is closed. Okay, so we already know that H is closed, and now so we know now that A bar is contained in H because it's contained in every closed set that contains A, right? So A bar is contained in H, but then we make the following observation. Now, notice that A bar must itself contain the set of limit points. It always does, you see, because every set must eat its limit points. And that implies that H is in fact equal to A bar. Okay? Because what did we do? We just added the limit points. Okay? So any closed set must eat all its limit points, otherwise it's not a closed set. And by showing that this thing is a closed set, then we are done. Okay? And that gives us, before you go, what does it tell us? Something really important. It tells us that a set is closed if and only if it eats all of its limit points. That's enough, okay? So all it needs to do is eat its limit points, and that's sufficient to be closed. Yes?
How about, does it work the inverse way with the interior way? Are the limit points excluded?
Well, to be open, it doesn't need limit points, right? It might include them or not. What is an open set? Think about it. It's like a Roman defense. What do? What do Romans do? They are not really what they do. They protect a certain region, and they might leave a few reserve soldiers to be killed by the enemy, right? Well, so to be an open set, what you do is that you are an attack, you retreat, you form a defensive line, and all those that are not part of your defensive line are lost. Okay, and that's what herds do. Okay, so a herd that wants to be perfectly protected. In other words, if you want to find the interior, what you do is you feed all the stray animals, all the ones that are not protected to the lions. The ones remaining are all surrounded and defended by bodyguards. That's what interior is going to work like. Good? Goodbye.